Chapter 5 covers continuous random variables. In this chapter, we will learn how to recognize and understand continuous probability distributions, how to find probabilities of events within a continuous distribution, and this chapter introduces us to continuous random variables in a manageable way. The remainder of the semester will largely be spent using continuous random variables as we discuss inferential statistics. Some properties of continuous random variables that we should keep in mind. The graph of a continuous probability distribution is a line or a curve. Probability is represented by the area underneath the curve, and the curve is called the probability density function, abbreviated as PDF. We will use f of x to represent the probability density function. Note that this function does not give the area. Area under the curve is given by a different function, capital F of x, called the cumulative distribution function. For those of you who have taken or will take calculus, little f of x is the derivative of big F of x. Most of you do not have calculus, so we'll have to find other ways of finding big F of x and finding probabilities by finding the area underneath the curve. Some more properties that you might need to know. The outcomes are measured, not counted. The entire area under the curve and above the x-axis is equal to 1. Probability is found for intervals of x rather than for individual values of x. The probability that c is less than x is less than d is the probability that the random variable x is in the interval between c and d. This is equal to the area under the curve between c and d. The probability that x equals a specific value is equal to 0. So that means the probability of c less than x less than d is the same as probability c less than or equal to x less than or equal to d. We will spend quite a bit of time this chapter discussing finding the area, and remember the area is the same as the probability. To find the probability by hand, you need to find the area. Finding the area is elementary if the curve forms a shape that we know an area formula for. Unfortunately, most continuous random variables do not form a nice shape that we know an area formula for. We would need to know calculus to find the area of these known shapes, but most of you don't have a calculus background, so we're going to use tables and calculator functions for quite a few of our random variable continuous random variable distributions. There is one, though, that we will not need calculus for and we'd be able to do by hand, so we get a bit of a grasp of what we're doing before we jump into the more complex continuous random variables. This first distribution is the uniform distribution. To help everyone gain a general grasp of continuous functions, we will start by looking at the uniform continuous distribution. The graph of the uniform distribution is a straight horizontal line. This allows us to form a rectangle between the line and the x-axis. Thus, we can find the probability nicely by hand using the formula for the area of a rectangle. Just a reminder, that formula is area equals length times width. We might look at it as length times height as we're looking at our graph, though. So just a question to make sure that you've been paying attention. The graph of the uniform distribution is shaped like, just said it on the last slide, a straight line. And because it's a straight line, we're able to form a rectangle between the line and the x-axis, which allows us to find the area, hence the probability by hand. So the uniform distribution assumes that the random variable can assume any value between a and b with equal probability. So some formulas you might need: f of x equals 1 over b minus a. The probability that x is between c and d is equal to 1 over b minus a times d minus c. You might need to know your mean. The mean would be a plus b divided by 2. And then the standard deviation of this distribution is the square root of the quantity b minus a squared divided by 12. So let's take some time and get familiar with this uniform distribution by taking a look at the graph of one such uniform distribution. The time it takes to wash dishes is uniformly distributed between 8 and 15 minutes. So that means f of x equals 1 over 15 minus 8, or 1 over 7. So if we were to look at a graph, we would have our y-axis and our x-axis, and we want to graph f of x equals 1 over 7. Now this is a horizontal line where y equals 1 over 7, and it specifically exists between 8 and 15. So that means this shaded area here would be all of the area between our horizontal line and the x-axis. That area has to equal 1. So now, continuing to use this distribution, the time it takes to wash dishes is uniformly distributed between 8 and 15 minutes. Let's find the probability that tonight it will take between 10 and 11 minutes. So we have our nice graph of our distribution. That lightly shaded area shows all of the probability that there exists in this distribution. We're specifically looking between 10 and 11, so that's that darker shaded rectangle that I just put on the screen. So the probability of being between 10 and 11 minutes is 1 over 15 minus 8 times 11 minus 10, which equals 1 over 7. Now, we could have just looked at our picture and said that we have a width or a length of 1. The distance between 10 and 11 is 1. And then the height of our rectangle there is 1/7. So the area then would be 1 times 1/7, which is 1/7. Let's look at example number 2. Example number 2 says the time it takes to wash the dishes is uniformly distributed between 10 and 17 minutes. What is the probability that washing dishes tonight will take me between 13 and 15 minutes? Using our formula, we have 1 over 17 minus 10 times 15 minus 3 equals 2 over 7, or approximately 0.29. Looking at example 3, the time it takes to wash dishes is uniformly distributed between 11 and 19 minutes. What is the probability that washing dishes tonight will take between 13 and 16 minutes? Again, using the formula, we have 1 over 19 minus 11 times 16 minus 13 equals 3 over 8, approximately 0.38. Looking at example number 4, the time it takes me to wash the dishes is uniformly distributed between 9 and 14 minutes. What is the probability that washing dishes tonight will take me between 10 and 12 minutes? Again, using the formula, we have 1 over 14 minus 9 times 12 minus 10, so 2 over 5, which is approximately 0.4. Looking at example 5, the lengths of a professor's classes have a continuous uniform distribution between 50.0 and 52.0 minutes. If one such class is randomly selected, find the probability that the class length is between 50.2 and 51.2 minutes. Again, using our formula, we have 1 over 52.0 minus 50.0 times 51.2 minus 50.2, giving us 1 over 2, or 0.5. The lengths of a professor's classes has a uniform continuous distribution between 50.0 and 52.0 minutes. If one such class is randomly selected, find the probability that the class is between 51 and 51.3 minutes. Again, using our formula, we'll come up with 0.3 over 2, which is equal to 0.15. Let's look at another example together. The time it takes to wash the dishes is uniformly distributed between 8 and 15 minutes. Find the mean and the standard deviation of the time it takes to wash the dishes. Remember, the mean is equal to a plus b divided by 2. So that means 8 plus 15 divided by 2 is 23 over 2, or 11.5. So the mean time it takes to wash dishes is 11.5 minutes. Now finding the standard deviation, we're going to do b minus a, square that result, then divide it by 12, and finally take the square root. So 15 minus 8 is 7, 7 squared is 49, 49 divided by 12, and then taking the square root, we get 2.02. Example 7. The actual volumes of quart-sized jars of Hellmann's mayonnaise are uniformly distributed from 31.53 to 32.5 fluid ounces. Find the average volume of a quart-sized jar of Hellmann's in fluid ounces. So averaging our endpoints, we have 31.53 plus 32.5 divided by 2, giving us 32.015. Example 8. The actual volumes of quart-sized jars of Hellmann's mayonnaise are uniformly distributed from 31.48 to 32.48 fluid ounces. Find the average volume of a quart-sized jar of Hellmann's in fluid ounces. So adding those two endpoints together and dividing by 2, we come up with 31.98. In example 9, we are now going to find standard deviation. The actual volumes of quart-sized jars of Hellmann's mayonnaise are uniformly distributed from 31.49 to 32.56 fluid ounces. Find the standard deviation in volumes of a quart-sized jar of Hellmann's in fluid ounces. So standard deviation should be equal to taking b minus a, then squaring it, divide by 12, take the square root. You should get 0.3089. And example 10, again finding the standard deviation. This time we're assuming that the Hellmann's mayonnaise jars are uniformly distributed between 31.42 and 32.51 fluid ounces. Finding the standard deviation, again taking b minus a, then squaring that result, dividing by 12, and taking the square root, we get 0.3147.